Right, I found it. All right. So the first thing, the first thing is we get our data from according to our student IDs, right? I'm sure we've done this part already.
Mm,
So here there was A, B. So these two
yeah.
values are the last two digits of your student ID. So those values FK, MK, VK, these are according to PET's solution. These are the standard combination value. Then
Mm,
apart from, so these are for the design. Then there's also the basic
mm-hmm.
value. So for the basic combination value, you multiply these values times 1.35. So for
Okay.
FK, you find F by multiplying FK by 1.35. MK, VK, same thing. Then from there to answer question one. So in question one, what we're trying to find is the embedded depth and also to choose the bearing stratum. So the layers, I think the layers they had and the layers we have are a bit different. For us, we had layer one, which was the miscellaneous fill, 0.5 centimeters thick. Then two was silty clay, which is soft plastic. I think this is the main thing. This is the main detail to look at. And then the next one was hard plastic, which so this is what made my decision, because we know from one of the PPTs, I think that should be somewhere chapter 3. Wait, let me there. That should be chapter 3,
Mm,
where it says that hard plastic is a better choice. So clay hard plastic is a better choice for our bearing stratum. So I think layer 3 is the best choice, because we have choices between 2 and 3 are the ones which been.
mm,
So I think 3 is the better option. So now that you've chosen that
okay.
3 is going to be the layer where you're going to place is going to be a bearing stratum. Now you decide like, okay, now what's my embedded depth? But then it just has to end in the it has to end in the third layer. So the distance from the top we have 0.5 here. Then after that we have 1.5. So
Mm,
the second layer, the total distance from the surface to the bottom of the second layer is about 2 meters. So your embedded depth has to be more than 2 meters. For me, I chose 2 point, mine was 2.5. So it can be 2.5, 2.1. The embedded depth doesn't affect many of the calculations apart from just the ones in question 2. So
oh,
yeah, anything is okay. I think just average. I think between 2.1 and 2.5. I've just heard someone else chose 2.1. Okay.
okay.
All right. So that's when you've answered question one. At that point, you've chosen your embedded depth and you've also chosen your bearing stratum, which first we've said is layer 3, clay, the hard plastic.
Mm,
Yeah. Then you can decide. I also decided to follow this just to help me think and also to to show the teacher to draw this, just to show at least which layer your thing is in, and also a
okay.
kind of to give, yeah, to just explain for your next calculation. So if you want, you can sketch this. I don't know if it's compulsory, but I think it's just a good idea. So now
All
get
right.
into question two. You want to say something?
No?
Okay. So getting to question two now, we have to solve for the bearing capacity. So for the bearing capacity, the method we're using is the standard chord method. We've got three
Mm,
methods for solving bearing capacity, and the one we're using here is the one for this formula. So for this formula, you're going to see that we need the FAK, we need I'm not sure what this thing is, NB, I'll call it NB. We need to find gamma. Gamma here is the effective unit weight at the bottom of the foundation at this point. Then B here is the breadth of the foundation, or the shortest distance in the case of a triangle, of a rectangle. So B is that distance. We need ND, which is also just, these are standard values. NB and ND are standard values which come from
Mm.
the choice of the bearing stratum. So we've got a table. So the fact that all of us are choosing this
Oh,
clip,
yeah, yeah.
these are the same. So this is standard. It's just FAK. Our FAK is different. These
Okay.
guys had 210, ours is 220. So for the sake of calculation, we assume that B is 3.5.
3.5?
I mean, three. We assume that
Okay.
B is 3. I think I wrote something else. So we assume that B is 3 for the sake of calculations, just so we can calculate, because we need B here.
Okay.
Yeah, so just assume that it's 3, because that really won't affect, because 3 minus 3 is going to cancel out here and we're going to get 0. So
Sure, yeah.
yeah, we just assume that it's 3. So gamma is the unit weight at the surface here. The unit weight, the effective unit weight. So effective unit weight is the unit weight, which is the Laushi said we can use 20 for all of them, minus 10, because this is below the water table. The water table is at 1 meter from the surface. So gamma
Okay.
here is 20 minus 10. Then the other gamma is the average. Can I call it average? Something like that. Over
Mm.
of unit weights from the top layer to the bottom, to this line. Let me say here, right?
Okay.
So how do we find that? How we do that is we multiply the gamma of each layer times the distance over the kind of depth, right? The embedded depth we've chosen. So I'm going to repeat that. Is the sum. Let me say, it's the sum of the unit weights of the layers, the gammas of each layer, times the distance of that layer. I mean the thickness over the depth. So, like
Okay.
for example, we can take what Faith did here. So for the first layer, right? Is this
Mm.
one? For the first layer, it's from this side. From the first layer, she's got a total thickness of 0.5 times this 17. I'm not sure. I can see. I think 1.7. Then the next one, which is 1.5 times 9, and the like. So the thickness, just consider we've got this in our case, we've got the first layer, which is 0.5, the next layer, which is 1.5, but then the next layer the next layer, consider that after 1 meter from the surface there's a water table. So about 0.5 of the second layer, I mean 0.5 of the second layer is dry, is not, is on top of the water table. So that one, the gamma is 20. But then the other, let me see, the second layer is how thick? The second layer is 1.5. So we're saying that from the first layer, this is 0.5 times 20. That is gamma. In the second layer, we've got 0.5 times 20. But then
Okay.
after 1 meter, so 0.5 plus 0.5, 1 meter. At that point of 1 meter, we've got the water table. So below that, we don't multiply them by 20, we multiply them by 10, 20 minus 10. So it's by 10. So
By
the
10.
calculation,
Okay.
let me just write that. Where's the pen? So for example, you chose, let's say if you chose 2.5, right? Like myself.
Mm-hmm.
So that's going to be 0.5 times 20. Sorry, 20 for the first one, plus the next 0.5. So we got into the second layer, but this is the part which is over the water table. 0.5 times 20. Then the next part, we're still in the second layer, but then this remaining 1 meter in the second layer is under the water table. So it's 1 times, you can say 20 is the gamma, but because it's under the water table, we say minus the unit weight of water, which is 10. Then we've said 2.5. So plus we've got also 0.5 in the third layer. So 0.5 times the same 20 minus 10. So I can just say 10, or you can say 20 minus 10 just to show the Lao Shi. Then all this here over the embedded depth. So this is your gamma M.
Okay.
So your embedded depth is a total of 2.5. And put the point there. All right. So yeah, so this is your calculation. Okay. So now we go. So that's that. Then at that point you've got your values for calculating FA. So we said FAK has been given to us is 220 if you choose the second layer. Then NB is 0.3. Gamma at the bottom is 20 minus 10. 10. B, we've assumed, or we said let B be 3 minus 3 there, plus ND 1.6. Gamma M will come from that calculation. I think I found something like 14. D is the depth you choose, the embedded depth you're going to choose. Mine is 2.5 minus 0.5. So yeah, this is the calculation. From here you find your allowable bearing capacity. So you've answered question 2. After you answer question 2, we go to question 3, where you want to find the size. So the dimensions, you want to find the length and the breadth of your foundation. So to make calculations easier, I think a bit easier to follow, as Faith did and I also followed, is to make your foundation a square, like same length and same breadth. Yeah, to make it a square, I think that's much easier to deal with than having to calculate for a rectangle where they might be different. So she used this formula, but then I think she could have used an easier one, which is that PPT. She could have used some other formula. That. So for a square, you can use this formula. It means it's going to give you directly what you can use for one side. So we have the values. FK is the value which you calculate according to your student ID. Stop playing with the spray. Put it there. So FK is the value for the value you find. FA we've just calculated. Gamma G is 20. D is the embedded depth. Gamma W is 10. Gamma H is the distance from the water table. I think they explained that somewhere here. Why is that? I'll give you that explanation. Oh, here is the distance from the water table to the bottom of the foundation. So in my case, that distance is about 2.5 minus 1, about 1.5. So it will depend on what you choose your embedded depth as. So this is the formula you can use. So you just find it directly, but Faith used this one and then had to again come to find B, which, yeah, it's just extra steps. So you can use that formula. Then Yeah. So yeah, you also add this factor. So you can add, I used 1.2 instead of 1.1. I saw some other, I think the other week you sent me, the guy used 1.2. So I decided at least I also get
Oh,
information
yeah.
from there. So 1.2 or 1.1, I used 1.2. But the same formula. So this is the formula for a rectangle. This one here.
Mm-hmm.
You can get the
Okay.
formula for a square, but she solved it as a rectangle in the end. So after, if you use this formula, what you're going to find is the area. That area, you're going to choose the kind of ratio you want to have between your L and your B.
Mm.
And in the case of a rectangle, it would be some other number, usually 2. But then because she wanted this to be a
Square.
square, because she wanted it to be a square, the number is 1, the ratio between
Mm.
L divided by B. So the formula for finding
Mm.
B then becomes the square root of the area divided by that ratio which you've chosen. In our case, is 1. So the value you found here, square root, is your B. And then L shanshan B. So this is the how to find it. But if you use that formula, the answer which you're going to find here is your B and your L, because it's the formula for a square. So
Okay.
after that, you want to check eccentricity. You want to check if the dimensions which you've chosen are okay to work with. So now for you to
Mm.
find that, that's okay. I'm going to join you. For us to find that, so Fk plus Gk, we have this formula. Again, gamma G is 20,
Mm.
the area A for area, D for embedded depth, gamma W is 10, gamma H is the distance from the axis, from the water table to the bottom of your foundation, or just
Yeah.
say the distance to the water table, which is 1 minus your embedded depth and the area again.
Okay.
So this is F plus G. Then MK here, this is her MK, but then she also added V
Mm.
times the H. V, V is a force going in this direction, like from here, something like, let me just explain that for the sake of,
Yeah.
let me see some people helping. All right. So yeah, V is like a force in this kind of direction, like shear force, let
Mm.
me say, and it's causing a kind of moment. So you multiply it by what you assume is the distance of your foundation, the distance from here to
Okay.
here. Yeah. So we just assume, we don't yet know. We're going to assume for the meantime and find out if it's
Mm.
correct. So what
Oh, okay.
Faith assumed, that what I've also followed, is that this thing is about 800. Yes. Thank you. This thing is about 800 millimeters.
Okay.
Yeah. So that's what she's using in her calculation here. So let me just. Where are we? Over here. Yeah. So that's when she's calculating MK here. When she calculated MK here, so 444 was the one from we calculated as MK from our student ID.
Yeah.
Then
Mm.
172 is V times that distance. We said 800 millimeters, which is 0.8 meters, to find M. So yeah, that's this part here. Then you've got E is equal to MK over over FK plus GK. I think you can just write, because this is not really MK, this is MK plus VK times H. So you can just write E is equal to MK plus VK times H over FK plus GK. And then from there you find your eccentricity. The eccentricity should be less than your distance, the L, whatever you've chosen to be your distance, over 6. So if it meets that, then it's met the first requirement. You check now against PK max. So PK max is equal to FK plus GK over the area, B times L plus 1, times open bracket 1 plus 6 times the eccentric distance over L. Then yeah, we check that. Then here, the value which you find from this formula should be less than 1.2 times your bearing capacity, or the allowable,
Okay.
the allowable load. So if it doesn't meet this requirement, then change your dimensions.
Okay.
Yeah. So just change your dimensions, and when you change your dimensions, it means that you also have to. So you change your dimensions, check again, check for eccentricity, check PK max, and then go back and also check bearing capacity. You get,
Okay.
because we've changed the dimension. So at this point, we've said it's not. This is the one we've chosen. So we go back and check if the bearing capacity is still okay.
Okay.
Put this new value. This part where there was B at first, remember we assumed to say it's 3, right?
3.
Yes, but
Yeah.
now from our calculations here, she's found that okay, for it to meet the requirements, I have to make at least 3.6.
Okay.
Yeah. So you can assume anything. For me, I went with 3.5. But then now I
Okay.
think 3.6 is better because according to what? That's building construction. Your dimensions have to be dividable by 3, like without leaving a
A
remainder.
remainder.
Yeah.
Okay.
Yeah. So I think that's why she went with 3.6. I went with 3.5.
Okay.
Okay. Yeah. So we proceed.
Yes.
And then what's next? Where are we? So all right, after you've met the requirements, then you can now go to the fourth question. So in the fourth question, we are trying to calculate the reinforcement. Yes. So in calculations of the reinforcement, we want to check first for punching force. If you remember that thing from the last assignment. So punching force was saying that if the column has a certain force, it might break the kind of foundation. Let me see if I can find an example of that. I think that's one of the last PPTs. This is the one which this is what we're following for the calculations for this part. This example here. Yeah. So the punching force is
Okay.
this theory here. Let me see, not this one. This one, to say that if it's got too much force, it's going to break in this kind of way. So this is what we're trying to solve for. The punching failure.
Okay.
Yeah. So we follow these steps, and those steps are what these steps here. So if anything doesn't look clear in the paper, maybe you can just refer to this. This is PPT 3.3.
Oh, okay.
Yeah. So, okay, where are we? So we're here. So the first thing is you want to check reaction of the force, which is the force times B times the area. Divided by the area. So here we're using F. If you've seen on top there, we've got FK and we've got F. The standard.
Therefore, yeah. The
The
basic
standard
what?
Shanshan and the basic combination. I think that's what it's called. So yeah, we calculate this F divided by the area. F divided by the area, we find the value here. We're going to use this. Eccentric distance is 0, M plus V H over F. We calculate there. And then, yeah, we check for, we're going to use this value. So here we're just setting up. And then it should also meet this requirement. When you reach here, it should meet this requirement. So it should be less than L over 6.
Okay.
Then yeah, with this formula, so the same PJ open bracket 1 plus 6 shan, the minimum is minus, the max is plus. We find this
Plus,
value.
yeah.
Yeah. So the first thing we want to check is the foundation's height. So we already assumed the foundation's height in that calculation while we said 0.8 or 800. So here we're just checking out if that assumption is all right.
Okay, okay.
Yeah. So at the columns H is equal to shan. Effective height was saying minus 50, I guess.
50.
Yeah,
Yeah, 50.
50, right? So BC plus 2H0, it should meet the requirement that BC is breadth of the column.
Wait, finding the effective depth, the protective cover, that's the one that's subtractive, right?
Yeah.
Can it be any, like, there a range for it? Maybe
Let
like
me
40
say
to
between
50.
35 and 60. I think that's what I've seen most values from.
Oh,
Yeah.
okay.
Yeah, between 35 and 60, something like that. All right. So we have BC plus 2H, BC being the breadth of the column. We've
Okay.
been given by Laushi, he told us 400 by 400 millimeters.
400. Yeah.
So which is 0.4 here. Just to check. So this one, the condition is that it should be less than B, the length we have decided for our foundation.
Yeah.
So here we've got a calculation to say PJ max, the value which we found here, right? We're going to use it a lot for the next calculations. So PJ max, open brackets, the brackets times A over 2 AC is one side's length of the column.
Okay.
Yeah, so they're the same. So there's AC and BC. One side is AC, the other side is BC.
BC.
Yeah,
Okay.
but then the Laotia is given as same. So 400 by 400. So that's 0.4 and also 0.4 here. H0 being the one we've chosen here. So all these times B. I made a mistake. I thought this was 6. So this is B here.
Oh,
Yeah.
okay.
So minus B over 2 minus BC over 2 minus H0 shanshan squared. So equals, you replace, you find that when you find this, what you do is now you check this formula. So this formula is 0.7 beta HP FT. So wait, I haven't, did she put her data anywhere? Oh, the data is here. So we've been given concrete, we've been given the concrete grade and the steel grade. So our concrete is C30.
Yeah.
Our steel is HRB 335. So we have FT and FY. These are the same for everyone.
Okay.
Yeah. So those are the values we're using here. So beta HP FT plus BC plus H0 outside the bracket, H0 again. So we have 0.7 B beta HP is 1. Then this is what, 1000. This is just
FT.
yeah, FT times 1000. And then these, yeah, so this should just meet the condition that the value here should be greater than the value we found from this calculation. The value you find from calculating here,
Okay.
right, should be greater, yeah. So if you find that it is, it means that qualifies, you proceed to the next thing. If it isn't, we have to change something here. So like what would we have to change? We can think of changing the heights. Yeah, the main condition we're checking for is the height of the foundation.
The
So
height.
yeah,
Yeah.
change the height. Try again until it meets the requirement. Okay, so we proceed. So now we're checking the first steps. The first step, why we're saying this is because as you can see, it's got steps, right? It's got this.
Mm.
at the first step. So we're talking about the first one we're calculating is this distance from here to here. That's what we've checked right now. Now I want to check from here to here, which is about half, so 400.
400.
Yeah, yeah.
Yeah.
Okay. So where are we? Where are we? We're here. So yeah, and then also the dimensions of that step, like how big is it? So we make assumptions first. So take the height of that to be 400.
Mm.
So the effective height 400 minus 50, which is 350. The length of that step is about 1.8 by 1.8. So
Mm.
L1
Okay.
1.8, B1 1.8. We've assumed, right? So now let's check if these
Yeah.
assumptions meet the requirements, or these dimensions we've given, if they meet the requirements. So again, the same kind of calculation somehow. So uh,
Mm. Yeah, it looks the same.
PJ max, yeah, I mean, yeah, PJ max L over 2. L1 is the L we put here, H0, this is B here,
Mm.
B minus B1, then from here, minus H01 squared. We check that. Again, same thing, 0.7. This thing is just what was changing. So this time it's B1 here.
Yeah.
So we check that
Okay.
it has to be that such that the value we find from here should be greater
Mm.
than the value we found from this calculation here. So if you find
Mm.
that,
Okay.
you've met the requirements. So we've met the requirements for height if you finished here.
All right.
Okay. So after that, now we proceed. We go to reinforcement computation. So reinforcement computation, this thing has
Mm.
been sectioned in certain ways from the example.
Okay.
Let me just go to the example for some context. So we have section 1.1, which is cutting through there.
Mm.
So it means in section 1.1 we have, like, okay, this is the foundation, right?
Mm.
Then this is the first step, and then this is the column.
Mm.
Mhm. So now we have section 1.1 and section 3.3 in this kind of direction. So section
Yeah.
1.1 is cutting even the step. So the height of section 1.1 is from the bottom of the foundation to the top of the foundation, which we said is 0. Is 800.
Yeah.
Then section 3.3 is on the first, from the first step. Let me call it the first step. So it's got a
Mm.
height of about 400.
Yeah.
Then in this direction, we also have two sections. We have section 4.4 and section 2.2. Yeah. So what we're going to do, the
Mm.
next steps
Yeah.
is we're going to, using these sections for our calculations, like trying to find the moments in this section so that we can calculate the reinforcement we need.
Mm.
Yeah. That's what the next steps are. So we're going to
Okay.
calculate using these sections, the reinforcements we need. So say starting in section 1.1. So section 1.1, we have what, PJ Shanshan. So PJ, remember those PJ, we
Mm.
calculated PJ max and PJ mean, right?
Yeah. Yeah.
So PJ1 is equal to PJ mean plus the distance plus this is the one side of the column over 2 times the
Mm.
open bracket PJ max minus
The
PJ mean.
maximum and the minimum.
Yeah. So we find this value. This value, we're going to use it to find the moment. So moment one over Shan PJ max PJI.
Mm.
I'm sure we know all the variables here now, right? Are you right with
Yeah.
me? Okay. So
You
you
just
find this
replace.
value. You find this value. She was
Yeah.
finding a new H0. I didn't get this part very much because from what I saw previously, we're using 50. But here she's using like 45. I just followed.
Yeah.
I don't know exactly why.
45.
Yeah. So I just followed suit.
Yeah.
I'm not sure exactly why it's that.
Oh,
So the calculation of
okay.
AS1 is equal to M. I mean the moment at section 1, then 0.9, the Fy, the H. You find this value. So you find this value, then you go to
Okay.
section 2.2. Section 2.2, same process.
Mm-hmm.
Same process. What was the difference? The difference is that I've forgotten the exact difference. I think in this formula somewhere.
Say
Huh?
the difference with the first one.
Yeah, let me see. Oh, here we've used AC. Here we've used the distance of the column. Then here
Mm-hmm.
we've used L1, which is the distance of the first step. That L1
Oh,
here,
okay.
Faith chose 1.8. And I also followed
Mm-hmm.
the same.
Okay.
Uh-huh. So
So you just choose any, right? Like, as long as it just works with it, with
yes, as long
meets
as
the
it works,
requirement.
yeah. And also divisible by
Okay.
3, I think.
Oh, okay.
Mhm. Don't even know why I forgot that point. Yeah. Anyway, so yeah, 2 times shan over that. We have we find our value here. M shan,
Mm-hmm.
same formula. It's just that we're using L1
Mm-hmm.
instead of AC here. And
Yeah.
even here, what did we use? Here we used BC, yeah, instead of B.
BC.
Instead of B1. So in section 2.2, when you see B1, it's talking about the dimensions for the first step, which is 1.8.
Oh, okay. Yeah. Okay.
And you find that you H0 still the height we chose minus 45. So we find that
Okay.
you find your AS 3.3. This is section 3.3.
That is section 3.3.
Yes. So when you find this AS, we choose the bigger AS.
Mm-hmm.
We found the AS for 1.1, right? We found the AS for 1.1 here, and we found the AS for
Yeah.
section 3.3 here. So now you choose the bigger AS. In our case, the bigger AS is the one for section 1.1.
One.
Yeah, so the
Yeah.
configuration of the reinforcement will be according to the AS at section 1.1 or area of steel at section 1.1. So the way you get this is this is like you have to design this yourself. You choose. So the first thing you can just choose is choose your diameter.
Mm-hmm.
Choose your diameter. Diameter can be anything, any of these diameters from this table. I'm using the table from
Design of concrete.
yeah, design of concretes, the textbook. So
Okay.
you can choose any diameter here, but I think the more common diameters are between 12 and 20. At first I chose a big one, and then it's I think these ones are better to use between 12, 14, 16. I used 14 and
Okay.
Faith also used the same. Yeah, they can find it. Okay.
Okay.
All right. So let's say we chose let's say we chose 14.
Mm-hmm.
Okay, yeah, let's say we chose 14. So 14, remember this table is the bar area per 1 meter length.
Mm-hmm.
But then the area of what we're choosing is about 3.5. So the first thing you can do is first we want to meet the AS. We want to be close to the AS which we've found
Yes.
here. Let's say, for example, Faith's AS for AS1 was about 3,000, 4,359.1. So
Mm-hmm.
whenever we choose, we want it to be close to that amount. So what we're going to do is we are going to, so remember this number.
Mm-hmm.
Then we're going to get any value here in the range for 16. That's easy to deal with, even the first one. So just remember,
Okay.
this is 16 by 1, right? So for 16 by
Mm-hmm.
1, the area is 20 201.1.
Mm-hmm.
This is the area. But then the area which you want to meet is about what? 4,300.
4,300.
Uh-huh. You wrote it. So yeah, 4,300 and something. So for us to find the number of bars that we need for us to meet that requirement with a diameter of
Mm-hmm.
16, we divide that value, that AS which we found, by this area here.
Mm.
Yeah.
So that's how you find the number of bars.
Yeah, that's how you find the number of bars. So
Ah,
we say it's hot here. Is it hot that side?
hot.
Huh? Yeah,
Oh no, it's freezing.
hey, I can feel something else. It's hot.
It's
So
freezing here.
yeah, so for 16, we're going to get that value and
Mm.
divide it. So let's see, why is that value? Or let me see this one first. So this is 201.1, 201.1. Let's keep that. Where's my calc? I can calculate. So that's going to be 201.1 divided by
Mm-hmm.
4,359. So 4,359.1 divided by 201.1. So the answer is 20, 21.6.
Mm-hmm.
21.6. So 21.6, 21.6. Or let me use 14 so that we can find, so that you can know how she got this same value.
Okay.
Yeah, let me use 14. So let's see what's the first value in the table for 14. So for
See 153.9.
okay, yeah, 153.9. So that's going to be this same value. So
Mm-hmm.
4359.1 divided by 153.9. So which is 28. So you round it up, not round off.
Mm-hmm.
Just round it up to the nearest whole number, which is 28.3. Let's make it 29. So we use 29 bars. So here she has put 29 bars with a
Mm-hmm.
diameter of 14. Then this distance here is so this is the spacing. So this is the meaning of this is what's your spacing between the bars. After one bar, what's the distance between them?
Mm-hmm.
So that distance is for us to find that distance, we get a pen. We say open brackets the distance of our foundation, which is about 3,500, right? It's 3.5 meters now
Mm-hmm.
in millimeters. Then minus the covering surface, and the covering surface is on both sides. So that's going to be 2 times 45 coming.
Mm-hmm.
You can find that one. It's this side. The follow space to it on the bike in the morning. A bit, but it can work. It can still work. So yeah, this divided by this kind of the number of bars minus 1. So 20, 28, I think something like this. This formula, I'm getting it from the PPT, the PPT for foundation engineering. That's why I saw this formula.
Oh, okay.
So this is about 5,000 minus, it'll be not 90. 90 divided by 28. Okay, mine's a big difference. Should go. There's nothing? Okay, I'll remove that date. Just help me. What can we do next? Just help me put these things back on the table. Then, yeah, so the value I found is 121, and that's what I would have put as my spacing. I'm not sure exactly what she used. I think she might have used maybe the same. Oh no, hers is,
Her distance is 3 6.
yeah, her distance is 3,600. So divide by 28. No, it's still much smaller. I'm not
Oh,
sure. I'm not sure exactly how she's getting hers. But this is this formula. I saw it from why did I say this formula? I've closed it. You can get this. It's for Cozy. Should give Cozy. Yeah, the formula is here. I mean, not here. It's in the assignment we had for design, for the module design for this same course.
oh.
Yeah, that's the one I'm following. I'm wrap this thing.
No, that's someone. How
Huh?
to find that?
What?
This is when I'm knowing, you know that. That's someone how to find this whole part, and the explanation is different. So that's the one I've been using all this while. I said the spacing. They just told me choose. I couldn't whatever works for your design. Like you just choose. So I never knew how to find the spacing. I just choose to
That's
choose.
what I was also
Yes.
taught, but then I was confused. But then
Yeah.
the formula is, where is it? Let me just. Why is that? Why is that? Why is that?
Maybe a number of bars.
Even the number of bars I just choose. Now, how do you just choose?
No, the number of bars you told me choose like the distance of your whatever you're doing the foundation. You divide by your spacing.
Oh,
That would be number of bars.
I finding this is why I found the formula. So something like this. Then this is the formula for the space.
Oh.
Ah,
So this, but I never understood it. I remember in that assignment.
I
I
can't.
just yeah.
Not to worry too much. The way we're doing assignments this time, can't understand them.
Yeah.
So
Okay.
the space you've chosen, like the area calculating for, minus the cover
Yeah.
space because it's on both
Yeah.
sides, divided by the number. We need a total of 25 spaces. So just the number of bars minus.
Number of bars. Yeah.
Yeah.
Okay.
All right. So now we proceed. So there you've chosen your reinforcement. I think we're even done. Oh no. So we've so remember that one and three are in one axis. Then in the other axis, so this is like, let's call it, I think, the y-axis. Then in the x-axis, we have section 2 and section 4. So
Yeah.
for these ones, we've got a total of about this is the formula. So this one is much shorter. So this one is just m2 1 over 24. PJ we found it some time back. Why is it? What do you here? The F over the area.
Oh yeah.
Yeah, this is what we found PJ.
Okay.
So PJ open bracket B minus BC squared over BC, the breadth of the column, times 2L, the length AC, the breadth of the column. You find H minus, here again she was using some different calculation which I didn't get. I don't know, maybe they taught them in class or however they were learning this guy. So here she was doing 45 again minus 14. I'm not sure exactly what this was.
Mm,
Mhm.
okay.
But I just followed suit to be on the safe side. Guy.
Mm,
So
yeah.
again, whenever calculating AS, so remember you get this value of M
Mm,
times 10 to the power 6 because
6.
we're calculating in newtons per millimeter.
Okay.
Yeah. So just convert those. Yeah. So you find your value here. You find AS for 2 for section 2 and then for section 4 do the same calculation. Here is just that instead of what is BC there, here is B1 and A1, which are 1.8, 1.8. And then you find your AS4 and you get that. Then there's also AS. So there's this AS, even I forgot. Let me see. Here, before you choose, after you've chosen your, what is it? You should do it. Did I get that from Faith? I think I did. Oh yeah. After you have chosen your design, your combination, after you've chosen this thing,
Mm,
you have to check if it fits the minimum requirement. So the minimum requirements that the still ratio should
mm.
be greater than 15%, 0.15%, I mean.
Oh, okay.
Yeah, so for you to check that, it's the still ratio you've chosen,
Mm,
then over. Oh, then, yeah, sorry. You've chosen your number of bars, 29,
mm.
right? Then you
Yeah.
go here. After you've decided your number, you go here, not this one. You go, like we said that we got this first value here, right?
Yeah.
So you're going to set 29 times this value. That's your AS. That's the AS you have decided to use.
Oh, oh yeah.
Okay, let me just check if that's correct. So 29 times 201.1. Yeah, which should be
Yeah. The number
something like,
of bars divide by that.
yeah, multiplied by that. So
I
that
mean, you multiply.
something like that. No, it's not giving me the exact same value though. Oh no, hers is 14. Yeah. I used 16 on this one.
Yeah.
Uh,
Yeah.
let me just check. 16, so 16, I mean for 14, that's 153 point.
153.9.
Okay, so it's giving us that value which is put. Okay, right, yeah. So that's what she chose. So then so the formula, so this is rho is equal to the value you've chosen for your AS here according to your design divided by
Mm,
this is 355 the effective height
yep.
times the distance,
Mm,
which is has is 3,600 plus 400 times 1,800. Then the value you're going to get from this calculation is going to be a very small number, like raised to the power 10, like on
mm,
your calculator. But then just multiply that number
mm.
times 100 because it's a percentage.
Percent. Oh yeah. Okay.
Yeah, so then you find this value. Then just if it's above 0.15, then it's okay. It meets the requirement.
It's okay.
Mhm. So we proceed. Yeah, then you also do the same. The same for the next. Here you do it in opposite. So instead of checking, we're actually getting our AS or one of our AS. We've got our AS2, our AS4,
Mm.
and then our AS is gotten from multiplying the the kind of area here,
Effective height.
yeah, times the still ratio, which is 0.15%. So 0.15% means 0.15 divided by 100. Multiply it.
Yeah.
It's not
Okay.
0.15, otherwise you find a big value, but 0.15 divided by 100. Then you check for the
Okay.
biggest one. So from the biggest one, you choose your
Mm-hmm.
design ratio.
Okay.
Yeah, then when you've chosen your design ratio, that's it. So according to the rules, you've seen how to choose the number of bars, how to choose the kind of spacing.
Yeah, now I've known.
So we're
I
good.
was doing yeah.
Okay, Bombo.
Oh, and the drawing.
Okay, so yeah, that's it. You know, this is what even takes me time because I failed to write an assignment where I don't get. So it takes time
Mm-hmm.
trying to understand each calculation.
Yeah.
So anyway, otherwise, how are you?
I'm fine.
You're fine.
At the end. Now what if I'm sick? Why asking me now?
Let me just. Okay, hello, hello, hello. Hi, hey. You've been calling? No, I haven't seen any calls apart from this one. Where on my line? You know my line is Kapal, right? No, you can't. I told you my line is Kapal. This is when he's just come home. This is when he's reached. Let me call you in a bit. I have a meeting right now. Yeah, you're walking back home. I'm coming. Just a bit. Don't go offline. Don't go offline. Hey Rose. All right. Achan, how are you? Sorry, I got.
Fine, Kaumi.
I want to
I'm
make
okay.
sure.
How are you?
I'm good. I'm all right.
Yeah.
Okay. All right
Okay.
then. So I'm going to send the recording.
Oh, okay.
Uh,
Thank you very much.